Well, let's see here. I will begin with a word of prayer. Dear Father, we, again, Lord, thank you for this time we have. Just help us to use it wisely, to glorify you in what we do, Lord. In your name I pray. Amen. So I would, I will lead off here before you ask me any questions with just, this is a theorem I'm going to go over next class. But let me just state it and show you how it works for a second. Ruffini. And it's pretty awesome, this theorem. It simply says the following. It says the order of a permutation sigma in Sn, all right? Where sigma is equal to, say, gamma 1, gamma 2, gamma k, all right? Disjoint. Suppose that those are disjoint cycles, okay, as we talked about last time. If you have a product, if you have sigma as a product of k disjoint cycles, then what's the order? The order of sigma is simply the least common multiple, all right, of the orders. It's the least common multiple of the orders of the gammas. And by the way, the order of a particular cycle, so like where, I mean, he states it a little bit better in Gallian. Instead of saying orders, he just says lengths of gamma 1. I don't think he has gammas in his theorem. I mean, I mentioned this last class, right? If we take, for example, 1, 2, 1, 2, so think about it. 2 goes to 1, then 1 goes back to 2, and so forth. And like, so this is the identity. So the 2 cycle has order 2. But if you look at ABC, I mean, let's just generalize it a little bit. ABC, ABC, what happens here? We'll start with A. Okay. I guess that's it. All right. Now what happens if we take ABC cubed? So that's ABC times ACB. What's that equal to?
A goes to C goes to A.
Okay. So A is its own island. B? Mm-hmm. Mm-hmm. In other words, it's the identity.
So hypothetically, we could maybe show that the order, like if you raise it to the power of its order,
I think we're assuming, I mean, I'm trying to think where we did it. I think we have, if you think about what you just did mentally, you were assuming that A, B, and C were what? Yeah, unique. They were distinct, right? Try this out for size. If we do 1, 2, 3, 2, right? 1, 2, 3, 2. What will happen this time? Okay.
Wait, how do we know whether it goes to 1 or 3?
Oh, you read the cycles.
Oh, so it goes to 3.
So yeah, one goes to 2 to start with, and then 2 goes over to here. Yeah, it goes to 3. Right, and then 3 goes to 2. 2 goes to 1. Oh, there. Right. And then now we start with 2. 2. Sorry, I have to read it from this way. So 2 goes to 3, right? 3 goes to 2. So 2. That's it. So this is actually the 1-3 cycle.
Do you technically have to do the second 2 also? Or do you already know?
Well, I mean, you...
2 goes to 1 goes to 2.
Again, remember what this notation means. It's, alpha composed of beta. And we have to think about putting x in here, right? But this is, of course, alpha of beta of x. But the kind of funny thing is, the way that works, of course, is, if I have a1, a2, ak, and I have b1, b2, bj, right? Not until 7.
Okay, so it begins at 7?
Yeah.
Okay, sorry for disturbing.
You're fine. No problem. I mean, if you got abstract algebra questions, I mean, I don't recognize them though, so it looked a little young. Excuse me. So, I mean, again, it's kind of the awkward notational. So you feed x to this, right? How's that go? So what happens is this goes over to here, right? And then you pick up on wherever it goes to, right? And then that goes over to here. And then whenever you get it, then if A3, then that goes to A3, and then it's equal to A3, So it's, but we only have to answer where x goes to for x equals 1 to n. So like, I figured out where 1 goes to. 1 went to 3. And then we figured out 3 went back to 1 again. And then the only thing left in this world is 2.
Right.
So we're done.
Okay.
So whatever else you're thinking, you're trying to say something intuitively about the notation which isn't there.
Okay.
Let's say it that way. Okay, but my curiosity here was, this is a cycle length 4. Does it have order 4? I have a suspicion that the reason that 1, 2 has order, I mean, look at this. Here's a stupid example. Check this out. Here's an even simpler example. 1, 1, 1, 1. 1, 1. Well, that's equal to 1.
So the cycle length
There's
is
a,
1.
right, that's a 2 cycle that doesn't have order 2. It has order 1 because it's not a real 2 cycle. It's a, it's not a 2 cycle with distinct symbols. My suspicion is that this will not have length 4 either.
Is that what will not have?
What's that? The 4 cycle we're looking at right now? I mean, let's calculate the cube. What do we get? 1, 2, 3, 2 times cubed, right? Would be 1, 2, 3, 2 times 1, 3, right? Because we just worked out that the square is that, so I'm multiplying the square by itself again. All right, so you want to start at 1? Very popular. 1 goes to 3, 3 goes to 2.
And then 2 goes to 3.
Huh. So you got 1 goes to 3, 3 goes to 2. Okay, and then what happens to 2? 2
Goes over there, and then it goes
to 1. Oh, so that's that. Huh. Well, what do you know? That's not, and 3 goes to 3, I would wager. Right? 3 goes to 1. 1. What? Oh, man.
Didn't you say that you start, so...
I did something wrong here. Sorry.
don't we start at the beginning of that first cycle? So
Goes to 3.
The 2, but 2 goes to 3.
Oh, yeah. Thank you.
That's what I was.
Yeah, you should be confused. It was wrong. Thank you. This, various educational professionals have told me that I had dyslexia at some point in my life, and I don't really believe it, but I do believe I have an inability to pay attention to detail sometimes. So let's see here. 1 goes to 3. Like you said, 3. I'm an idiot. Let's try that again. 1 goes to 3.
3 goes to 2.
3
so
goes
you
to
put 2
2.
in there, and then after 2 should be 3. Because
2. Oh, 2 goes to 3. Oh, I see. Oh, that's it.
and then 3 goes to 1, which goes to 2.
Yeah.
So it shouldn't be 1, 2, 3, 2.
3 goes to 1. Then 1 goes to 2. So 3 goes to 2. Oh, weird. So you're saying it's 2 again? What? Oh, man.
Confusing having that extra 2 in there. Isn't that against it being 1 to 1 and not 2? Having an extra 2.
That's a good question. Am I allowed to write that? Oh, wait a minute. You shouldn't let me do that. We can't even write that. Doesn't even make sense. I'm sorry. I'm an idiot. Well, I'm an idiot. I'm sorry. I almost want to go start the tape and stop and start the tape again. Golly.
Then isn't even it? Wait,
Yeah.
Does that mean it's 1 to 1 or does that mean it's not?
Right, because this is notation, right? For the array. Oh, well, it's complicated what it's for, but
Because 1 can't go to 2.
right, you shouldn't be able to repeat a number in a cycle, right?
Yeah, because 2 can't go to 1.
I'm an idiot. But I did that last class, didn't I?
No.
I didn't. Okay, phew. Whew. All right, well, I just have to erase the tape here and we'll be fine. Goodness gracious. Ay, ay, ay. I am so sorry. All right, well, now that we have got that out of our system, I think you can convince yourself that a k cycle has order k. Right. So this is forbidden. Well, I guess that still makes sense, though. Let me shut up. All right.
1 goes to 1.
Let's deal with cycles with unique numbers. Yeah. Sorry. Now, but that's not to say that the number can't be repeated in a formula for product of cycles, right? Because you can do stuff like
Right. just
1, 2, 3 is equal to like standard trick 1, 3, 1, 2. Or you can write 1, 2, 3, 4, 5, 1, 5, 1, 4, 1, 3, 1, 2. So what's the pattern? I'm not thinking through it. I'm just using a pattern, right? So first of all, it's like this with this. That's that one. Then it's this with that. It's this one. And then it's that one. And then finally it's that one. So it's like 1, 5, 1, 4, 1, 3, 1, 2. And then you can try it out. Send 1, 1 goes to 2, 2 goes nowhere. So 1 goes to 2. Send in 2, 2 goes to 1, but then 1 goes to 3, 3 goes nowhere. 2 goes to 3. And so you see this. So in that way you can rewrite any cycle as a product of, these are called transpositions, 2 cycles. So, and the Ruffini theorem wouldn't apply here. Like these are not disjoint cycles.
Right.
So this has order 5. And I mean, the least common multiple of these, order 2, length 2, length 2, length 2, length 2, least common multiple would be 2. But I think, is that right? If all the numbers are the same, is the least common multiple the numbers? What's the least, how do you define least common multiple?
If you do prime factorizations, isn't it?
For example, what's the least common multiple of 7, 49, and 7?
Because 49 is also multiple.
It's 49, right? So the LCM of 2, 2, 2, 2, 2 is 2. Okay. Sorry. But anyway, the point is that that has order 5. This does not have order 2 because the theorem doesn't apply. But if we were asked, like, what's the order of something like, if we had something like 1, 2, 3, and then 7, 9, and then 8, 10, 11, you start needing commas when you get bigger numbers, right? If that was your permutation, then what Ruffini's theorem says, if you want to calculate the order of that permutation, since you've got it in disjoint cycle form, all you got to do is calculate what's the least common multiple of the lengths. Yeah. Or if you have something that's not in disjoint cycle form, right? If you've got something like 1, 2, 3, 4 times 3, 4, 1, right? Your first move would be to rewrite that thing in disjoint cycle form, which we could do, since this is actually an honest, like, I don't know, actually maybe that was productive to do that because we saw that we couldn't do it, right? It didn't make sense, that other thing, so we can't, it actually is nonsensical. I mean, because it's easy to write that in the cycle notation, right? But if you go back and think about what that means for the array notation, we're, like you said, we're violating that it's a bijection. I think it's actually not, saying that violates it being a function, because we're saying that 2 maps to 2 different values. I mean, so, okay, so we start with 1, as is our custom. 1 goes to what?
3 goes
3.
to 4.
Okay, and then what?
4 goes to 1 goes to 2.
Okay,
2 goes to 3.
okay.
3 goes to 1.
3 goes to, okay, you got it? And then what do we have next?
That's everything.
Oh, okay, so order 4.
What was your purpose in doing the squares and cubes?
Oh, I was just calculating the order directly. I was trying to show you that a 3 cycle had order 3, a 2 cycle had order 2.
Okay.
We could do the calculation directly with 4 distinct elements and show that a 4 cycle had order 4.
Okay.
Anyway, I just thought it'd be helpful to say a couple words here about that, because a fair amount of the homework that's due Monday is about orders of permutations, right? And that's all pretty much this theorem.
And Monday we have 2 groups of homework.
Mm-hmm. I think some of those are easy.
Okay.
But, well, I mean, some of them are from Gallian. So, like, if I remember right, I've assigned let's see here, where did I put it? Let's see here. I said complete the Cayley table for S3. Now that you're getting fluent in the cycle notation, that should be a breeze. We started doing that here, right? For each of the following permutations, write the permutation as a product of disjoint cycles. I think you should be able to do that. Find its Write it as a product of transpositions and state whether it's even or odd. And then I'm pretty sure after Friday, all of those questions should be like pretty straightforward, if they're not already. I mean, I'm going to look at those questions with you now if you want to in a second here. Gallian number 10 is really not a question about permutations per se. It's really just it's a Math 200 question really. Show that a function on a finite set itself is one-to-one if and only if it's onto. So I'm assigning this problem because I think people need to review what one-to-one and onto mean some more. And then 35, how many elements of order 5 are there in A6? So what's A6? Now, of course, we can go back and talk about other stuff if you want. I don't know what you're...
Right. The only question that I had was just one step in the proof of the fundamental theorem of...
Cyclic groups? Sure.
Okay, basically... It's on page 47.
Uh-huh.
Okay, so the one says, thus A to the QT and A to the K are an H.
Now, are we in part 1 or part 2 or part 3, the proof?
Part 1, third paragraph.
Third paragraph in part 1.
Top line, where it says, thus R equals 0. As
See.
T is the smallest element.
Top line.
I'm just wondering why R has to be 0.
So let me just. I'm going to read the line leading up to that. So I have note AT is an element of H, right? Implies that A to the minus QT, which is, by the way, A to the T inverse raised to the Q power, is an element of H. Thus, A to the minus QT and also A to the K are elements of H, right? But remember that A to the R is equal to A to the minus QT times A to the K from the line above, right? So that means that A to the R is an element of H. Okay? But what is R? We applied the division algorithm. We have K is equal to Q. I mean, R and Q's fates are linked, right? K is equal to QT plus R, where 0 less than or equal to R is less than T by the division algorithm. Okay, so this is an element of H, right? But notice that R is either a positive number less than T or it's 0.
Okay.
But if R is a positive number less than T, that would say that it's an element in H, right? It's A to a power R, where R is less than T. But T is the smallest power which appears in H.
Oh, I was thinking T was the order or something like that. Okay.
No, you get, so the lambda, it's the set of possible powers.
Okay.
It's a little bit sneaky. So like T is the smallest element. That means A to the T is like the smallest group element in some sense that appears in H.
Okay.
And if A to the R was not, if it was anything other than E, it would be an element which was in some sense smaller than A to the T. where I'm now saying smaller as it relates to the a to the thing. But I mean, the smallness is in lambda. Lambda is a subset of the natural numbers to be, yeah.
Okay.
Yes, I know. I have had that feeling before. It's like once you see it, it's like, oh, oh,
Yeah.
oh, okay. Now we can go on with our lives. All right, so. So let's think about, I mean, I like these sessions because I don't have to, I mean, we're not under a lot of time pressure, so we can just kind of play with stuff, which is nice. So one of the things I haven't, all right, so how would you find, I mean, first of all, you know that the inverse of this guy is just that guy, right? I mean, this is equal to 1. And so more generically, if A and B are, well, I guess, again, A and B must be, it's assumed, right? Let us be reasonable individuals. Let us assume that if we're writing, you know, I have not said this, but I'm assuming this. In the last class, I made proofs about like alpha, which was A1 da 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 AK or something like that, and beta was B1 da 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 BK. It is assumed that the A1 through AK are distinct. Otherwise, it wouldn't be a legitimate cycle, as we have been forced to learn today. And but my point is, then this is 1, right? So therefore, AB inverse is just AB, right? But how about for a 3 cycle? Oh man, I shouldn't have erased that.
Yeah, I think it was ACB.
Was it? Yeah, so this squared was ACB? Okay. So of course that, and then so that means that ACB times ABC is what?
We had
Right. I'm going to check it again. A goes to B, B goes to A, good. B goes to C, C goes to B, C goes to A goes to C. Okay, yeah, the identity. So therefore, let's see if we can see the pattern though. I don't know if I can see the pattern yet. ABC is their pattern to ABC, ACB. It's not just the, I mean, I feel like if we write it in cycle notation, right? I mean, like in this kind of notation, right? Doesn't it feel like if this is sigma, then this should be sigma inverse?
Yeah.
So like sigma would be A goes to B, goes to C, goes to A, right? Sigma inverse would be A goes to C, goes to B. Oh, whoa. But maybe it's easier to see what's going on here, right? If we write this as, or is it? I don't know. I'll start with C. This is C, B, oh man. See, I'm writing these the wrong way. This is BA, isn't it? Do you care to make a conjecture? You can tell me. If I have A1, A2, da 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 da, AK, and I want to find its inverse, what is it?
AK.
I bet that works. By the way, I think that's a problem in Gallian. Which problem was that? It's like, was that stupid? I think I saw that. There's a homework problem in here somewhere. Oh, maybe I didn't. I don't know.
You said it was one of the ones you wrote down.
Oh, Oh, there it is. It's number 30. What have I done? What have I done? 10:35. Okay. We're okay. I'm worried. I'm a little worried about this. Where's my other one? That was lecture 8 homework. Where's my lecture 9? I still got to finish typing chapter 9. Oh, phew. I've also assigned number 40 and exercise 1 on page 111. Exercise 1. Look at exercise 1 on page 11. So, thank you. I mean, you're welcome.
Thank you.
Yes, you should. Yeah, well, you're welcome. Yes. Exercise. Exercise 40. Prove that Sn is non-abelian for n L(n) greater than or equal to 3. You got to come up with an example that works for arbitrary n larger than 3. So that suggests to me you probably can make the numbers 1, 2, and 3 and some cycles involving them not commute. And those are not just in S3, those continue to be non-commuting in all of the higher Sn which they're contained in, right? Because like S3 is naturally, in some sense, included in S4 and so forth and so on. That problem's not bad. You just have to think a little. All right, let's take a second here and prove this guy. If I have time. Do I have time?
It's 5:23.
5:23. Okay, we're fine. Now, where this starts to get fun, I mean, this just you just write them in opposite order. That's great, but that only works if it's what? All right, so let's start with A1. And what happens? A1 goes to AK. AK goes to A1. Then A2. A2 goes to A1. A1 goes to A2. Eventually we'll get to AK. AK goes to AK minus 1. Right? And then where does AK minus 1 go? Back to AK again, right? Yeah. Now, to prove that carefully, I should do induction, right? But we got 5 minutes, so I'm just going to leave it at that. Here's an engineer's proof of it. So, but how would we invert something like this, though, right? What if I had 1, 2, 3, 4, 7, 6, 5? And I wanted to say that sigma, calculate sigma inverse. How would we do it? So this is alpha, this is beta, right? Just give them names. What happens when you invert a product?
It's B inverse A inverse.
Right, we use this, right, the sock shoes. And then having done sock shoes, then we go back to our, straight cycle reverso trick. So beta 5, 6, 7, and alpha inverse 4, 3, 2, 1. And it doesn't even matter if alpha and beta are disjoint or not. If there was a 4 here, for example, it wouldn't change much. Just puts a 4 here. But if I wanted to find the order of sigma, right, then I would have to do some work. So sigma would be equal to what? It's equal to, let's start with 1, goes to 2, 2, goes to 3, 3, goes to 4, 4, goes to 7, which goes nowhere, 7, 6 goes, and 6 goes to 5, right? 5 goes nowhere. And then we go 5 goes to 4, 4 goes to 1, close the cycle. Oh man, well, I was hoping to non-trivially apply Ruffini, but apparently not. So like, you know, if I had 1, 2, 3, 4, 7, 6, 5, which is a 7 cycle, right? And suppose I also had, I don't know, there we go, thank you, 8, 9, 10, then if this was a permutation, the order of gamma is the least common multiple of 7 and 3. 21. Now you were wondering what AN is. So basically the lion's share of next lecture is going to be spent proving that every permutation can be written as a product of transpositions. Okay. It's really that trick I just showed you not long ago, that you can just like this can be rewritten as A1 AK, A1 AK minus 1, dot 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 dot, A1 A3, A1 A2. This identity basically is the whole deal. I mean, we'll prove the identity element is even. Even or odd. Even means that you can write it as a even number of transpositions. Odd means it can be written as an odd number of transpositions. So, for example, the identity versus 1, 2, 3. So like, well actually this is even. 1, 2, 3 is 1, 3, 1, 2, even. If you look at 1, 2, 3, 4 though, yeah, 1, 4, 1, 3, 1, 2, this is odd. It turns out it's pretty obvious once you internalize this. If you take even times odd, you get odd. If you take an even times an even, you get an even. If you take the product of two odds, you get even again. Because you have like odd number of transpositions and an odd number of transpositions. You string them together, you get an even number of transpositions.
Is transposition just mean a 2-cycle?
Yes, transposition is another term for 2-cycle. I try to use both in here because both are used. AN is a subgroup of SN. This is just the subgroup of even 2 cycles. This is even permutations, rather.
What does AN mean in words? Is it just
it's the so-called alternating group. It's the alternating group, which, if I do well, I will explain in the notes when I write the next page in lecture 9 I haven't written yet. But even without explaining that, we can do problems in it. So you're asked, like, how many elements of order 5 are there in A4? So A4, what's that?
It's A6 in the problem, but you probably don't want to do that.
Oh, okay. So, but A4 is a subgroup of S6, right? And I could say, like, how many elements of order 7? Well, I'm sorry. But if you think, what does this look like? A4 has things like the identity, because the identity is even. And in S6, it also has stuff like 1, 2, 1, 3, or 1, 2, 1, 4, or 1, 2, 1, 5. I mean, I'm not sure this is going to get us anywhere. It's got things like that. There's a lot of things in S6. Oh, let me just hit the pause button on what I'm doing at the moment. S6 has 6 factorial permutations. All right? Oh, I mean to say S4. Even so, S4 has 4 factorial permutations, that's 24. Gallian mentions at the end of the section that the number of things in the alternating group is half. So there's n factorial over 2 alternating ones. So there's going to be 12 things in this list. So I guess I could keep going and figure them all out. But you can either have a product of 2 transpositions or a product of 4 transpositions, I suppose. It might be easier to think about them in terms of cycle, though, because this is like 1, 2, 3, or you could have 2, 1, 3, or oh, I'm an idiot. Let me just undo it. So that's 1, 1, 4, 2. This one is 1, 5, 2. This one is 1, 6, 2, I think.
What were in S4?
Oh. I'm sorry. Anyway, I'm not sure how to answer that question right off the top of my head, but I have to think about that more. But it's these things, so I have to think more about it. I don't know what to. I don't know good advice to give on that problem just yet. Are you good on the subgroup diagrams?
Subgroup diagram.
The lattice diagrams?
Oh, I think so.
Okay.
Yeah.
Yeah.
One with the primes, I didn't quite know how to prove that, the simplest subgroup generated by Q would be like a subgroup of the one generated by Q.
Yeah. Well, I will hopefully write reasonably decent solutions to all these problems. Seems like I have a mountain of homework I need to do, but I shall do it. Anyway, thank you for your questions. Maybe someone will send some more questions sometime soon. I am really, really happy with how well the class is doing right now. They have no questions. They must be doing fantastically right now. It's really, really encouraging to me as a professor.